VLF radio listeners, this one's for you. This antenna design aims to simplify DIY while boosting performance. Welcome back. Our video series on one-turn loops, also known as low-impedance loops, has sparked a ton of interest. And we just want to say thank you. Your comments, questions and contributions have been fantastic. Today we are building on that momentum with a new construction for an improved BALUN. The original idea of using choke ferrite cores wasn't bad, but let's be honest, it's not exactly DIY friendly. We have tested a bunch of options, and today we are sharing what we have learned, including some smart simplifications to make your build easier. Getting professional-grade PCBs for your project has never been easier. Whether you're a hobbyist or an experienced engineer, PCBWay makes the process smooth, fast and affordable. The company is offering an impressive range of products and services, from prototyping to full assembly. Check out PCBWay's website to get excellent support for your project. Take the easy way with PCBWay. Earlier simulations of the antenna's frequency response were showing that there is an optimum transformation ratio for each range. Our new approach is utilizing 3 secondary windings, allowing us to cover a larger frequency range with consistent sensitivity. When zooming in from 0 to 300 kHz, the simulation predicts that we can cover this range evenly. In our earlier designs, we switched between 2 baluns to minimize parasitic capacitance. With a tapped winding, we would lose the advantage. No matter where we connect, all parasitics would be connected to the signal path. That's why we are using 3 separate windings instead. Let's call them secondary 1, 2 and 3. We only need 1 primary winding and no longer need a switch. This avoids contact resistance, causing signal loss at the low impedance. Furthermore, thick wiring to the switch is eliminated. Now we need a clever circuit to connect the secondary windings. On one hand, we need to connect them in series for different ratios. On the other hand, unused windings must be disconnected from the signal path. 2 double changeover switches do the job. In the VLF switch position, all secondary windings are connected in series. In position LF1, the 2 lower windings are in series, and for LF2 only the middle one is used. Unused windings are separated. Our antenna shall be optimized around 130, 70 and 15 kHz, and corresponding transformation ratios TZ are 16, 80 and 400. Turns ratios T are the square roots of TZ. Here are the dimensions of the ferrite core. I link you to the source below the video. We want to determine the turns which, when combined, will achieve the desired ratios. Experiments were showing that 5.5 turns are working fine for the primary winding. Let's assume we had these options to combine the secondary windings. We are varying the turns S1, S2 and S3 until we are obtaining the desired ratios. Even though the equations cannot be solved exactly, the values found are fitting. Actually, there is a fourth option giving T4 equals 244. Let's call this mode VLF2. Maybe it improves the signal at around 35 kHz. The coating of the ferrite core insulates and prevents the copper wire from being damaged by sharp edges. We can use 0.5 mm wire, which doesn't break easily during manual winding. It must be cut to the required length before starting the smallest secondary winding. Fix one end with tape, wrap the wire around the core, and fix the other end as well. A few drops of superglue will hold it in place. When hardened, you can remove the tape and trim the wire ends to about 15 mm. Repeat the steps for the second and third winding. Next, solder on flexible cables and insulate the joints with heat shrinks. Transparent tape is protecting this first layer. Now the primary winding is wound over it. I used 2 parallel power cables to reduce loss and improve coupling. Finally, secure it with a cable tie. These are all parts you need. Ring nuts are clamping the loop's cable lugs to the M4 terminal and are serving as strain relief. Markings for drill holes are easier if you stick a post-it on the spot. And here is a cool tip for attaching the UHF socket. First, cut out a hole using a 16 mm hole saw. Then precisely align the socket, glue it in place with superglue and let it harden. Now you can drill the mounting holes and secure the socket with M3 screws. If you want, you can seal it from the inside. Before assembly, we are soldering lugs to the primary winding. Cables from the secondary windings are soldered to switches and the UHF socket. Finally, fix the balun in the box with adhesive. Then insert the gasket into the groove and screw the housing together. Please don't underestimate this. I strongly recommend using different wire colors to connect the windings in the correct orientation. Finally, we are clamping the loop and our antenna is ready for use. Connected to my RSPdx receiver, I'm now switching through the 3 modes. It looks like the antenna is adapting to the 15, 70 and 130 kHz ranges. As suspected, the 4th mode is also making sense. I'm switching now between 2 VLF ranges and now between 2 LF ranges. You can label the switch positions like this, for example. We built the balun with a toroidal RF ferrite core. Its performance in a certain frequency range is comparable to our previous designs. But it's outperforming by adapting to 4 frequency ranges instead of 2. And it is easier to build and assemble. There's still a lot to discover though. We received comments with interesting ideas, which we will explore in the coming videos. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.